So, okay, let me give a formal introduction and then I'll continue. Is my voice audible now? Please let me know.
Sorry?
Is my voice audible now?
Yes, sir.
Okay. Um, yeah. Okay. So, good evening, everyone. I am Shouharda Ghosh, a first year PhD scholar from the electrical engineering discipline at IIT Gandhinagar. I am presently working in the audio signal processing lab of this department. I have completed my dual degree, BTech as well as MTech, in electronics and electrical communication engineering with specialization in microelectronics and VLSI design from IIT Kharagpur. This is a NPTEL based PMRF TA session on the course Real Time Digital Signal Processing offered by ISC Bangalore, and this session will be held every Monday from 7:30 to 9:30 p.m. Okay, so you were asking me about this 12 this practice session thing. So let me tell you what I am planning to do. It's that if you look at the course videos of the past run, if you look at the course videos of the past run or even this one, as the weeks will proceed by, you will be able to see that slowly and gradually the theory content will decrease and the practical content will increase, the coding and all those MATLAB and CCS code composer studio type things, those implementations will increase. So what I will be doing is that as and when the time progresses, there will be more lesser things to say and more things to practice. Okay, so what can be done is that we have 12 weeks, so already this is the third week going. After the FFT and all these things are over, then you will have these application oriented things where I will be having very less things to teach or revise in that scenario, and even lesser problems to solve. Most of them will be practically oriented, and as you very well understand, in this platform also I won't be able to use either MATLAB or Code Composer Studio. In that case, what I will be doing, as you correctly pointed out, I will be solving the problems, okay, the problems of the previous portions in greater detail, and if required, and in fact vast majority of the content that is being evaluated is actually from the architecture design, filter design, these that I taught yesterday, that's the previous week, feed forward pipelining, retiming cut set, and all those delay blocks, architecture arrangement. Okay, so these are the things that I'll focus more in the later halves, when you will have lesser and lesser things to actually practice, to actually teach in other ways, when they're application oriented stuff. And apart from that, these 12 weeks, just before your exam, we will have another 1 hour session, okay, on where we will revise the things that we have learnt, and we will practice some more questions. Maybe we will be practicing some of the questions that were asked in that have been asked in this runs assignments. In fact, I'll be if time permits, I'll be solving a few questions from this the previous week's assignments, that whose answers I guess have been released. Okay, so that's the plan, and if you have any other suggestions, do let me know. Okay, you can send an email, you can shoot me an email. So just just wanted to know from all of you, how were you guys able to solve the previous week's assignments on your own? Anup, Raj, yeah.
Yeah, sir, can you repeat it again?
Was my voice inaudible as of now, or is it, or
It's
whatever
audible. It's
it's
audible.
audible, right? So
Yeah, yes.
what I just said was that how was the previous 2 weeks assignments? I mean, were you able to do it on your own, or did you face any difficulties? And did your
Yeah,
Uh,
yes, sir. Yes, sir. Two last two assignments was not good.
Anup, I guess, acha, okay, so not good in the sense that you So what was
I
the
am facing, sir. So basically, I am facing problem to solve the assignments questions.
Yeah, I understand you are facing an issue, but first of all, have you seen the lectures and understood the theory completely?
Yes, I watched the video lectures,
Okay.
but yes, sir.
Yeah, you watched the video lectures, but were you able to solve everything from whatever you had learned in the video lectures? I mean, since I will be taking up some questions regarding the week 1 and week 2 assignment, then it will be clear, because you had told me in the previous session that since you are a it's your second year going on, okay, so it will be a bit difficult for you to actually progress further. It means difficult in the sense that it won't be impossible, but since you have just learned signals and systems, or you're just learning signals and systems, and have you done discrete time signal processing course?
Yeah, yes, sir. Yes, sir. I have learned signal systems very well. Sir, concept is clear, and in last two problem sessions, you have already discussed deeply about IIR filter and FIR filter. Sorry, sir, FIR filter.
Hmm.
But sir, when I solve the problems, but I am facing some problems, sir.
Okay, so
Yes, sir.
what I can do as of now is that let me directly I have some of the assignment questions, so maybe I can directly jump into that. Okay, so I'm not I'm after solving the previous assignment questions, maybe then I can start with the okay. So are these the questions? I mean, these the ones that you can see?
Yes.
Yes,
Yes,
sir.
these
Yes,
are the
sir.
questions.
Okay, okay. Hmm. So let me start with the
Can you go to the third one? I had a doubt in the third one.
third one.
Assignment one, question three.
Assignment
Yeah.
1 question
The
3.
speech signal is,
The speech
yes,
signal is
this one.
sampled
Speech
at
signal,
8
yes.
kilohertz, so the Nyquist frequency is 4 kilohertz. Therefore, the filter cutoff should be okay at or below. Acha, your filter should. So basically, what is happening? Okay, so what was the answer that they given? Can you just confirm? I mean, what was the issue over
Oh,
there?
yeah. Actually, I also posted on the Google group. So the answer given is at or below 4 kilohertz.
Okay, and what is your guess?
Sir, we know that the Fs should be greater than or equal to 2 times of Fm.
Mm-hmm.
And sir, 2 times of Fm is Nyquistic frequency, sir.
Mm-hmm.
So sir, the answer will be at or below 4 kilohertz now.
I exactly. So I hope, yeah. So I will be explaining it in a bit detail. So actually, let me give a scenario of what actually happens. Okay, so this won't be a this won't be a dry course. I will, as and when I say the problems, I will also be giving real life implementation of what actually happens in real life. Anytime you see that my video is not proper, video is not coming, audio is not clear, please let me know. Okay, yeah. So
Sir, your voice is clear, but no, I think, sir, can we speak loudly because
is it clear? Hello.
I think you need to keep your microphone closer, I think.
Okay.
yeah, yes, sir, yes, sir.
Okay, fine. 2 hours. Okay, fine. Anyways, so what I am trying to say over here is that, is it perfectly fine now?
Yeah,
Yeah,
this is
yes, sir.
better.
Okay, okay. Yeah. So actually, I'm connected to my laptop. Huh. Okay. So the question was, you have some kind of a speech. It doesn't look like speech. Sorry. So the question was, you have some kind of a speech signal. Okay. So
Hmm.
speech actually comes in some discrete, you speak some words and you get these kind of local areas of fluctuation, and then some gaps, because we don't speak continuously, there are gaps in our words. So that's why you get these sort of, if you even see in detail when you record voice in a voice recorder, you will be able to see these kinds of envelopes, and each use, and if you study in detail about audio speech processing using looking at the envelopes, you can even determine the words that you have been speaking. Okay, so let's get to the point back. So you have this speech signal x of t, and you have sampled it at fs equals to 8 kilohertz. Okay, so what is happening is that what you actually do is that once you take your voice through the mic, okay, so you pass it after, let's say a mic, you have an amplifier, and then you pass it through a filter which is called the AAF, or the anti-aliasing filter. Okay, so far so
Okay.
good. Is this clear?
Yes.
Yes, anti-aliasing
Yes,
filter.
sir.
Okay, good. So then after this we have the sampler at fs, sampling them at discrete intervals of time, and then you have the a to d converter. Now you look at this what from a signal processing perspective. Let's say our speech signal, okay, is something like this. Actually what happens is that your speech, even though it's we have this speech components getting lower and lower amplitudes at higher frequencies, but then they do not die off to completely to infinity, huh? There will be some finite amplitude. So in order to avoid aliasing, we actually use some kind of a filter, some kind of filter. This is the aliasing filter. Let me say that's minus fl to fl. Okay, and now once we filter it, we get something like this, minus fl to fl. So now let's see what happens after sampling. After sampling, what happens, I guess you must be knowing, is that you will have replicas of the original signal, minus fl to fl, fl, here it's fs, so fs minus fl and fs plus fl. So I am assuming that this is a ideal low pass filter which has its cutoff fc at, okay, fc is fl only. So what we want to do, we want to ensure that we sample properly, so there should be no overlap. Okay, now in order to ensure that there is no overlap, what is the condition? This left hand side should be away from the right hand side, so fl must be less than fs minus fl. So fl, or you can say fc, what can we write? 2 fl upon fs. See, this is not we are solving a problem the other way around. Our fs is fixed and we are being asked to solve fl. So what do you see? Fl is less than fs by 2. So you see fs was how much? 8 kilohertz. So your fl, or the lpf low pass frequency cutoff, has to be less than 4 kilohertz. So the correct answer then turns out to be at or below 4 kilohertz. What was the answer set?
No, sir. This answer is wrong.
Or what did they mention?
Just one second, sir.
Yeah, please let me know.
The answer is at or below 4 kilohertz
So it's
itself.
correct. If it's at,
Yeah, I had it, but yeah, I just had a doubt that. But now I understood the explanation. My
okay.
doubt was like if you set it at 4 kilohertz, in that, I mean, if you set it less than 4 kilohertz, in that case, you're missing some frequencies that is at 4
Frequencies.
kilohertz, right?
Yeah, you are missing the frequencies, but when you are talking about an ADC, yeah, okay. So actually, what is happening is that when you are talking, if you are missing out frequencies, that,
Mm-hmm.
and you are missing out frequencies at the higher end. Okay, actually
Yeah.
most of our voice is contained in the low frequencies. and if you miss out a few, I mean when you miss out a few in 3 kilohertz, you may miss the higher pitches, okay, but a lot of our speech is
Got it.
actually concentrated in the lower one. But you see the danger, what will happen if, let's say, my frequency, the filter cutoff was, let's say, 5 kilohertz, okay. So what happens is that my signal lies between minus 5k to 5k, okay,
Hmm.
x of f, and when I sample it, now see the danger that lies ahead. So here you go, it's minus 505, all frequencies in kilohertz, and then you have a sampling first replica coming at 8, the center. Now you're shifting it from here to 0 is going to 8, so where will minus 5 go to? Minus 5 plus 8 is 3.
3.
So you see the danger, what is happening over here. This is even more
So
dangerous
yeah.
than losing. This is even more dangerous than losing a few 3 kilohertz. Okay, you will you start having this aliasing. Okay, so basically it was a very simple question. You see in gate, or some if somebody is preparing for gate, so it is a very nice way in which they can evaluate your understanding. So each one of us knows that fs is greater than equal to 2 fm, and if you see the past year gate questions or whatever have been asked in interviews or whatever, they mainly focus on setting the sampling frequency. But see how interesting, rather than talking about the bandwidth, they talked about the cutoff of the low pass filter. Okay, so it was very interesting, and it was like a bouncer question. Okay.
So why is 3 kilohertz dangerous actually? Can you just go back to
No,
that?
no,
But
3
like you
kilohertz
said,
is not.
3 kilohertz is
I
like
pardon me if I said 3 kilohertz, but I said greater than. I mean, if you go higher than 4 kilohertz, I mean, if your cutoff
Mhm.
frequency is greater than 4 kilohertz, let's say 5 kilohertz, you see what is
Yeah.
happening over here, aliasing.
Okay, got it. Yeah, there's an overlap.
There is an
Got it.
overlap, and you get garbage. That's worse than getting just of a lack of information. You get unnecessary stuff. So I
Thank you.
hope, yeah, welcome. So I hope this is clear to all. And any other in doubts with the
You said problem number 4.
problem number 4 of the first assignment? Okay.
Yes, sir.
Assume 4-bit fixed point hardware uses the fractional complement x1 equal to 0.125, x2 equal to minus 0.5. Okay, let me write that down. See, these are I must say, since it's an MCQ, you could have directly done it, but I'll show you both the ways, because if you sit for some interviews, then or in your grand viva, you may be asked these questions. Okay, so how do we represent this in, let's say 0.125 is 2 to the power minus 3. Okay, so when you're talking about 4-bit fixed point, and in most of our discussions we are talking about numbers between minus 1 and 1. So what we have, a3 dot a2 a1 a0, here power is 2 to the power 0, 2 to the power minus 1, 2 to the power minus 2, and 2 to the power minus 3. Here it will be 0 dot 0 0 1, and here's minus 0.5. You can write it as minus 1 plus 0.5. I'll tell you another technique to do that if you want. And then, so minus 1 means a3 will be 1 1 0 0. Okay, so let's see the cheating technique, I mean the shortcut technique, if you want to apply this in your exam, although these questions won't be given anymore now these days, people know the answers. So it's 5 plus 5 7, it's minus 0.375, and when you write that down, it's minus 1 plus 0.625, and that's minus 1 plus 0.5 plus 0.125, that is 1.101. Now if you want to add them also in binary, what you get, 0.001, 1.110, 1011. Okay, so both the answers are matching. So this I have done this very fast. Now Anup, let me know if you have not understood any step in this problem. Which step or which point are you facing difficulty in, or which problem part of the problem did not let you solve this correctly, or anybody else if you
Oh,
face.
no, sir. I
Okay,
understand, sir. Thank you, sir.
welcome. So you did you understand? Okay, so let's say you have an let for everybody's revision. What I can do is that how to convert the decimal number to the binary number, that I will give you in a short way. Let's say you have some number 0.27532. Now I want to write this in 4 bit. Okay, 4 bits fixed point. So it's implicit that I will be writing, unless and otherwise mentioned, first bit will be the MSB will be for the sign, and the last 3 bits will be for the fraction. So what we do is that we take the number 0.27532. If it's positive, if it's positive, we will do this, multiply that by 2. What do I get? So I have a calculator with me. So it's 0.55064. Check this place, this after the decimal place, whether it's 0 or 1. If it's 0, copy that 0 over here. Now the remaining part you bring over here and add a 0. 0.55064 into 2 you do. Now what do you get? 1.10128. You get a 1 over here. Now copy that 1. Now remove the remaining, add a 0, put the decimal place over here, the contents after the decimal point, again multiply by 2. Okay, so what do you have? 0.10128. So this is 0.20256. So these are the 3 fractional bits, and since this is a positive number, your MSB will be 0, so it's 0.010, and if you check the value, it will be 0.25. So what happened is that this is quantization error. So basically you have understood how to do this, right? Now in case I have a negative number, say minus 0.27352, what I will do, write it as minus 1 plus something. Okay, minus 1 plus something. What is that something? Obviously it's 1 minus 0.27532, which turns out to be 0.72468. Now you have minus 1 plus 0.72468. Now you perform the same steps that you have done earlier, like 0.7246 times 2 you will get 1, and all those. Let's say 1101, you got something like this, the same way that you have done over here. You kept on multiplying them by 2. You check the place up to the left of the decimal point, whether it's 0 or 1, keep on accumulating them, and this is, you accumulate it like this. Okay, so this is the after 0.010. So had it been something like 1101, you have obtained something like this in this order, then we will write it as 0.1101. And let's say you have minus 1 over here, so what will we write if we have, in case you do it with a negative number, 1.1101. Okay, I hope this is clear with everyone, how to convert a decimal number to a binary number.
Yes, sir.
Okay, very good. Now we
Thank you, sir.
welcome. So for option A, 1.101, I hope this is clear with everyone. Okay, any other doubts in this set of questions, 4, 5, 6, 7? No one. I hope everybody is clear with this. Okay, anybody has any doubt? Wait, did the slides move? Wait, I guess it's a bit, yeah. So does anybody have doubt in this portion? 1, 2, 3.
Yes, I have a
Yes,
doubt
sir.
in the first
First one.
question.
First one, right? Okay, so the first one requires a concept which I will be teaching now. Okay, once I teach that concept, we will again go back to this and then solve. Okay, in that way your this doubt is solved, and today and a good portion of today's class is also being done. So our agenda for now, thank you for raising this, is frequency response from pole 0 plot. So if you remember your analog electronics class, we used to have some function in say S domain, and we used to have something S minus um, S minus Z1, S minus Z2, all the way till S minus Zm, and then we used to have something like S minus P1, S minus, yes, so somebody raised a hand, oh no, okay, S minus P2 in all the way till S minus Pn. Okay, so Z1 till Zm we used to call them as zeros, and P1 till Pm we call them as poles. Okay, and what we used to do is that whenever you see a Z1, we move up by 20 dB per decade, and whenever you see a pole over here, we move down by 20 dB per decade. Okay, so we used to look at the pole position over here, 0 and pole location, and then move up and down, but here we will be talking about digital filters. Okay, and in digital filters our biggest thing is that our frequency lies between 0 to pi. Okay, and what is our frequency plot over here is the Z domain. So we have the real part of Z and imaginary part of our Z, and the most holy and sacred portion of this DSP is the unit Z circle, unit circle mod Z equal to 1. Now we will be dealing with real systems, so let's see in very fast way how what happens when we have a, okay, so in a digital system, whenever you have a pole anywhere, okay, a pole, let's say Hz equal to 1 upon Z minus A. So whenever you have Z equal to A, or you have a number very close to A, your H of Z will blow up to infinity. Okay, blow to infinity. So what does that mean? A pole works as an amplifier. Okay, a pole works as an amplifier close to the frequency corresponding to that pole. Now you see, on the other hand, if we have H equal to Z minus A, or Z minus B rather, where B is a 0, when we put Z equal to B, H of B goes to 0. So what does the 0 mean? 0 means attenuation, no signal, signal lost. So a 0 is like a attenuator or stopper. Okay, so it stops. Unlike, the funniest thing over here is that here a 0 used to promote the gain and pole used to dip down the gain, but over there it is the other way around. Now let's see some simple cases and try to see what happens. Let's say you have a pole over here, and since we are dealing with real systems, we'll have conjugates, and the best way to think about it is that you are a person, obviously you are a person, 0. Okay, so I need some of your help. So if this angle is 0, what is this angle? Can anybody tell me? What is this frequency in the Z domain? Z omega, we told, lies between 0 to pi, and then it repeats. So what is this angle? Can anybody please tell me? Anup Pandey, Rajshi Tapase, Saranya, Shashank, Siddharth, Sonali. Any idea what is the angular frequency at this point? Okay,
Sir, at which point?
this point. Can you see? Can you see my at this point? What is the angular frequency?
At this point,
Huh?
angular frequency.
Yes.
I think so. 2 pi. No, no.
Well, actually, no. If you, it's simple, a complex geometry. So let me revise certain things for you. This is our z plane, real part of z, imaginary part of z, and then our z can be written as r e to the power j omega, where r is the magnitude, omega we call it the phase, or in phase in general terms, and in this case it is our angular frequency, and omega will range from 0 to 2 pi. So how we go over here? Omega equal to 0, and always we move anti-clockwise. You have learned this in
So it's
math.
pi by 2.
Pi by 2, good. Here we go, omega equal to pi, and then again repeat, and we get omega equal to 2 pi. Now in general, whenever we do frequency response of digital filters, the area of interest is, I would not say this portion, but rather this portion. Why? There's a reason behind this, and the reason is that I just a few moments back shown you this diagram, right? 0 FM, then Fs, something like this I have shown, right? Do you remember, everybody? I have shown this diagram,
Yes.
that in order to ensure that your um, in aliasing does not take place, this should be FM should be less than.
Yes.
Okay, so what is actually happening is that you are sampling, okay, and in your sampling the range of frequencies that you allow is 0 to fs upon 2. Okay, so there is a mapping from continuous domain to discrete domain. And what is that mapping? If our continuous domain frequency we show as small f, and our discrete domain as omega, so what is happening? Our f will lie between 0 to fs upon 2, where fs is our sampling frequency, and omega will lie between 0 to. Okay, so what actually happens is that when you start from here, it is 0 frequency, and as you move along this line you start increasing your frequency, and then as you reach over here you actually end up reaching f equal to fs upon 2. That means you have reached a maximum frequency. And after that what happens is that you see over here, if you know everything from 0 to fs upon 2, from fs upon 2 to fs is mirror image. Is that clear? One second, let me repeat. If we have something like this and we are allowed to sample up to fs upon 2, if you have any kind of thing like this, then from 0 to fs upon 2, then from fs upon 2 to fs you will have the mirror image. And why does this happen? This happens because of the symmetry. This is a real signal, and this is the symmetry property of the real signal which causes this thing to happen. Okay, you can try and prove it. And in fact this is also the reason why 0, and it's like a full circle from here to here, you see it is completely repeating. So here 0 maps to 0, fs is mapped to 2 pi, and fs upon 2 is mapped to pi. Okay, so 0 is like low frequency, and since we are can be taking up to a maximum of sampling rate by 2, this is the high frequency. So in digital domain, omega equal to 0 and frequency is close to it, are termed as low frequency. Frequencies around pi by 2, which is close to fs upon 4, are termed as mid frequencies, middle range, and omega equal to pi, which then turns to fs upon 2, is termed as high frequencies. Is everybody clear with this? Any doubt at any portion?
Yes, it's clear.
Okay. Others? Anup, Rajshri, Saranya, Shashank, Sonali.
No, yes, sir. Clear, sir.
Clear, right? So you understood zero maps
Yes,
to.
sir, clear.
Good, good. So 0 maps to the frequencies in the low range, and pi maps to the maximum. So that's why now let me tell you a trick. What is, whenever we do frequency response, okay, whenever we do frequency response, what is the frequency response when you do? We do h of e to the power j omega. And what is that? This is the impulse, sorry, the z transform evaluated on the unit circle. That means I stand on this, okay, I stand on this circle and I keep on moving throughout this circle, okay, I keep on moving throughout this circle, and whatever value I get by, I stand over here, see the omega over here, I calculate h of e to the power j omega over here and plot it in a value. I see what is omega equal to 0 over here, I calculate h of e to the power, I see h of e to the power j0, I plot, I plot, I keep on seeing the value, I see, keep on plotting, I keep on seeing the value, I plot it, okay. So this is how you do, you go around the unit circle, keep on seeing the values and then plot it. Now you always keep in mind you are on the unit circle and you keep on moving and checking the values. So now whenever you see a pole, always think that this unit circle is like a paper, okay. This is an infinite z plane, okay, it's made of paper, and there is a unit circle, okay, which is lying above the ground, okay. This is a ground, this is a infinite paper, this is 1 unit, let's say 1 meter above the ground. Is this clear to everyone? Is this analogy clear? Let me know if the analogy is not clear. I will continue based on this analogy. This is the ground, football ground or cricket ground. You have placed an infinite size paper above that ground by a distance of 1 meter. Is that clear to everyone?
Sir, can you repeat it again?
Okay, okay, let me repeat it. So let's say you have a stadium, okay, let's say you have this stadium in your city or wherever you stay, okay, and then somehow all of your friends in college have made a very large paper, okay, sheet of paper, very large sheet of paper that can cover the stadium. Is that clear?
Yeah,
Yes,
yes, sir.
Okay, so
but
you have,
but yeah, I just had one question. Like
hmm,
you said that this paper is large and like infinite kind, and it's like on 1 meter from the ground, right? So the question is like, are you considering that it's flat, the ground is flat, or are you considering the spherical
everything is flat,
ground is
everything
flat?
is flat, everything is flat, okay. This is just I'm giving you this
Okay,
analogy in order to understand some concept which will be really good to easy to understand, okay, the pole zero
got
thing,
it.
okay. So you have this paper, now you put a reference over here. Let's say you say that at this, since a circle does not have any starting or end, so you cannot never say which is the start or end, but somehow you start and put a chalk over here and say, okay, see, this is my omega equal to 0. Now whenever I reach at this point, I will understand my omega equal to 0. Once you know which is omega equal to 0, your point you have started, you automatically know which is omega equal to pi or 2 pi. So what you have done, you have this sheet of paper and you have drawn a circle of radius 1 meter, and you have marked a certain point on that circle, and that we have seen as omega equal to 0. Once you know omega equal to 0, you can draw your axis, right, x and y axis, okay. Now we do the following assumptions. Whenever you see a pole, Now what you will do, you will start from omega equal to 0, you will keep walking on this circle. Okay, you will keep walking on this circle until and unless you reach back this omega equal to 0 point. Clear? Now whenever you have a pole, what will happen? From the ground, a pole, a metallic pole. Okay, you have seen the pole bars in the street, which in light posts in the street. So a pole bar will come out from the ground and it will stretch the paper. Okay, and the paper is elastic. Now another different, it might sound crazy, but it will be very useful. The paper is elastic, so the point at which there is a pole, let's say our pole is over here, so what will happen at that point? The height of the paper will go to infinity, and as you can understand very well, as you move away from that pole, distance will decrease. Let me show it even more clearly. So actually what happens is that whenever you have a pole, you have a very high value, and close to it the values start decreasing. Okay, but you see they are much higher than the ground side. Okay, the ground is over here, but these values are much higher. Okay, clear? Any doubt? Feel free
Yes.
to know. Okay, now pole is a pole bar, a lamp post or something like that, and a 0 is like a shot put ball. Okay, what will shot put do? Shot put is heavy, so wherever you place the shot put ball, it will come, and you can understand very well what will happen. It will touch the ground. Okay, this is the ground. The paper remains as it is, but since it is elastic, you can understand very well when you play these in these elastic nets, in these children keep on jumping, right? I don't remember the name of that thing where these children keep on
Trampoline.
trampoline. Yeah, thank you, thank you. So there is a trampoline. So trampoline only at the point where the pressure is maximum, that goes down, very down, right? And in the rest of the place it remains as it is, assuming that the trampoline is elastic. So similarly, like the trampoline, whenever there is a short put wall, it touches the ground. And so finally what we plot is there, in the h of e to the power j omega, we actually plot the distance from the ground. Okay, so let's suppose this is our z plane and we don't have anything, so it's simply a straight line, 1, don't have anything. Now let's suppose our first thing, let's suppose I put a it's too close, I put a pole over here. Here it's 1, here it's 0.8. So can anybody tell me what will happen from 0 to pi? Okay, so this is 0, this is pi by 2, this is pi. From pi to 2 pi, as I explained earlier, you will just flip the image around the pi, okay, like a mirror image. It would be even more difficult. I think it's better if I explain in a rather different manner. Okay, so let's suppose our poles are over here. Oh, it's not visible, sorry. Our poles are somewhere around here. Let's say the angles are pi upon 6, and here is my pole. Here is my pole. Okay, so what will what do you think will happen? So see here,
At pi by 6, it will increase the amplitude.
so actually what is happening is that there's a very big pole at pi, close to pi by 6, but since it's not exactly on the circle, so you will not go to infinity. You are around here, you have some height, you have reached here because of the pole nature of the pole, it gets stretched up, and as you reach pi by 6, since it's not lying on the circle, you will not go to moon. You will reach a considerable height, but you will not go to infinity. So you go high, and then you have reached the pinnacle, and as you go away, the depression comes in, means there's no more height, and it keeps on, you start moving away from the pole, so it will keep on decreasing. Okay, understood?
Yes.
So pi by 6, you see what happened, there's a peak. So in general, and since it's a real, so you will have another pole over here. So now you can understand very well what will happen if I put my poles over here. 0, let's say it's 3 pi by 4, so pi by 2, 3 pi by 4, pi, whenever you have a pole at 3 pi by 4, close to that, your peak will happen and it will fall. And then the closer your pole is to this unit circle, the greater will be your peak. So let me illustrate that with a diagram. Case 1, okay, you can verify them with MATLAB also. Case 2, case 3 is very close, and then this is the danger case. You know very well I am saying, why I am saying, I mean I can't even draw, I am not even allowed to draw this, because there's a pole on the unit circle, and you know very well that once it's unstable, we can't have anything called frequency response. Okay, it's almost like reaching the moon. Okay, so it's very clear now what will happen when you have a pole. Now let's look at what will happen when you have a 0. Okay, let's have a 0 over here, I have a 0 over here, pi by 6, pi by 6, 0, pi, pi by 2, pi by 6. Okay, so I am coming here, I am moving well, moving well. Suddenly as I move close by, you see that the depression comes in, this one is pulling things towards ground. So because they are pulling things to a ground, it will come down. But see, I am walking on a unit circle, and I am not encountering the shot put ball directly. Okay, the shot put ball is close to me, but it's not directly on my path. That's why I will not touch the ground. To some extent it will be there, and I will again go back. So I hope this is clear. Please let me know if it's not clear. And I will
Yes, it's clear.
now I will show what will happen when you have multiple poles, sorry, zeros. This, so at this point, same, see the pole location is same, but radius is decreasing. This, when you have close to over here, this, and when you have completely over here, you have this, it touched 0. Okay, so now I hope you have, everybody has understood what happens when you have a pole and when you have a 0. The pole amplifies and the 0 attenuates. Okay, so now let us see, let me tell you what was the question that we are solving. We had something like this, it was 5, then there was an adder over here, then there was a unit delay goes over, there was another 5 over here, I am sure, minus this was a xn, this was, am I correct? Was this the one that was there? Let me check once. Yeah, there's a 5, there's a unit delay, there's a unit delay, there's a 5, good. Let's see. So what will be the transfer function? Yn equals to 5 times xn, and these are 2 unit delays, so 5 times x of n minus 2. Is this one clear? Is this part clear? How I wrote this?
Yes, sir.
Okay. Anybody who is not clear about this, why I have written this?
Yes, I had a doubt. So,
Okay.
if it's 2 unit delays, why don't we have two terms actually, like minus x minus 2 and then minus x minus 1 as well?
Yeah, so actually why it's happening is that you see over here, here's an x of n, x of n minus 1, x of n minus 2. So basically I am not using this x of n minus 1 directly. Had I done something over here, this would have, my x of n minus 1 would have come, but simply when, because I'm directly passing that to another register, I'm not tapping into it, that's why this x of n minus 1 term is not coming. Did I clear your
Okay,
doubt?
got it. Thank you.
Okay, because there
Yes.
are two registers in series, and that intermediate register value is not being used, you are again transferring that to another register. I hope you understand. Delay means a register. Fine. Okay, so let me take the z transform. Y of z is 5 x of z minus 5 z to the power minus 2 x of z, y z 5 1 minus z to the power minus 2 x of z. So what is this called? This is called the transfer function of the system. Now what should we do? H of z is
We should multiply by the conjugate, right?
y. Y is the conjugate coming over here.
Multiply numerator and denominator by the conjugate to get the magnitude.
um, Actually here we are dealing with z. We are not, I'll tell you what is happening. We are dealing with z only. Okay,
Oh,
so
okay.
I'm showing, I'm making this clear to you. So here what I do, 1 minus 1 upon z square. This I'm doing it in a very simplified manner so that everybody understands. Z square 5 times z minus 1 z plus 1 z, z, z square. What are the poles? Poles are at 0 comma 0. Where are the zeros? Here is
1 and minus 1.
1 and minus 1. Good. Now when I draw, okay, so the poles are at 0 and 0. And what did I tell you long back? That as pole moves towards the unit circle, it starts showing its dominance. Okay, you get closer and closer to moon. But as pole moves away, okay, as pole moves towards the 0 position, the effect becomes negligible. And as you move exactly at 0, the center origin of the real circle, the pole does not show any effect. Be it 0, be it pole, there is no effect. Okay, so the zeros are at 1. Okay, real z, this is the unit circle actually, imaginary z, and this is the minus 1. So you have 2 points, 1 and minus 1, that corresponds to omega equal to 0, omega equal to pi. And what did I tell you? 0 is an attenuator. So when I start plotting h of mod, actually mod h of e to the power j omega, what do I see? When I start my journey, I see a short put on my path. Okay, and short put on my path means it has touched the ground, so it will be 0. And when I end my journey at minus 1, which corresponds to pi, because e to the power j omega, e to the power j pi, which is very well minus 1. And as I end my journey, there will be a 0. Okay, in between, as I move away, I will have, I will be moving away from this. So as I move over here, I see I become further and further and further away from these zeros. Okay, as I move away, I become further and further away from the influence. And so basically what I have is something of this kind. My lower frequencies are attenuated, higher frequency are attenuated, band is allowed as it is. So what do I call it? It's a band pass filter. And I have, this was the answer that they had mentioned, right?
Yes.
So everyone, is it clear now?
Yes.
Very good.
Yes, sir.
Yes, sir.
Very good. Now I will give some exercise for you guys. You have to tell me what kind of filter is it. Okay. So in common terminology, what kind of a filter would you call it? Wait, no. Wait a second. Wait a second. In order to make things even more clear, what I'll be doing. Actually, you don't design as using one or two poles. In order to have a better response, you do some kind of manipulations. Yeah. Can anybody tell now? This is the 0 and this is the pole. Can anybody tell me what kind of filter is this? Think about it. What is the pole doing and what are the zeros doing? Any speciality? Can anybody feel what is happening over here? Okay. So you see over here, as I told you a few minutes back, that whenever you have a pole, yeah, somebody wanted to say something. Any idea?
I think this is band pass filter.
Absolutely. But is it a normal band pass filter that I showed, similar to the one that I showed you, or something different? Do you feel anything different from this? Means will
I
it be?
think in this it's a very narrow. The band is very narrow.
Absolutely correct. Very good, Shashank. So what is happening is that I told earlier that this at pi by 4 you have you'll have a peak, but then you see I have lots of zeros over here. Okay, these are several zeros over here. Okay, several zeros over here. So what happens that in order to ensure that your peak is very high, you attenuate things very fast. Okay, you attenuate things very fast. So it's a very narrow bandwidth kind of a band pass filter. So you're almost like extracting one single sinusoid. Means you want to take a pi by 4, somehow that pi by 4 may correspond to some, let's say you are calling over a phone, and you want to catch your phone friend's signal, and let's suppose, I'm not a communication system expert, but let's suppose the frequency corresponding to your friend's frequency, sorry, the frequency corresponding to your friend's phone is at pi by 4, let's suppose. And in order to, but then you are getting, you have lots of signals in the air. I have my Wi-Fi on, I have somebody else's phone coming in. Okay, so there are lots of signals around me moving around, but then my mobile phone has to capture a single signal, right? So what do? I design a very narrow band pass filter. It's almost like a single filter that, almost like a filter that absorbs that pi by 4 frequency and does not allow anything near it to come. Okay, so similar to that, you may also have something like this. So basically what will be there will be some kind of a pole, and the higher number of, okay, so you keep on moving closer and closer, you get sharper and sharper responses. This is called a notch filter. So you are attenuating some components. So you may know that there are jammers, and jammers are there in various places, so they block particular frequencies. You may be blocking a wide variety of users, or let's say, there's in a college somebody is intentionally jamming or distort playing with your Wi-Fi. Means somebody is doing some nuisance, and you get to know his frequency. So what can you do? You can immediately tune the coefficients of your receiver or something, so that you notch his filter. Okay, so maybe if any one of you is working on telecommunication systems, so you will be knowing these things far better. Actually, I'm from VLSI background, so I don't have much on the much information on this.
Actually, Jammer, I think it works on the principle of interference rather than filtering.
Okay,
Because you need
okay,
to
okay.
generate a signal of the same frequency which you want to suppress, and then because of interference it suppresses the other signal,
Okay, okay.
because the one we are generating is of higher amplitude, right?
Mhm.
So that will suppress the other signal.
Okay, okay, okay. Yeah, you might be correct. I don't have much idea about this, but then there are other applications as well. Let's say in image processing as well. You want to, oh, yeah. Let's suppose you very well know that you have these ECG measurements being taken, but then we always have these 500 hertz electric signals. You know this, right? Everyone knows of these 50 hertz hum of these electrical three-phase signals, pure electrical transmission.
Yes, the
Yes,
power supply,
power supply,
AC
absolutely.
power supply
DC power
signal.
supply that has that 50 hertz ripple. So in order to, and that interferes with the biomedical signal measurements when you take. So what they do is that in a lot of papers and on a lot of implementations, they actually have this notch filter which simply cancels out this 50 hertz harm. Okay, that was an application. So yeah. So any other doubts apart from the first one? First one we have covered to a great extent. Two, number three. No issues on this. Good. Any issue on this? Was everybody able to
Yes,
solve
sir. Number 5.
five? Right. Okay. Okay. So yeah, you were the one who was asking me about this one in the previous session. So let me have a look at this. So there's, okay. So there was this x of n, and please let me know if I'm drawing the structure wrong because I have to refer to this multiple times. X of n, so okay, there's two delays and two delays. Oh, good. There was an line delay. There was another line delay. I guess it's a two-dimensional signal that they have been talking about. There was a delay. There was a delay, and then as usual, our multipliers, our pretty old FI filter structure, and then this was repeated, right? Okay. So from this delay line it goes over here. From this delay line it goes over here, and then how many was there in one adder and two adders? Okay, so there are two adders. Okay, normal one. So you have this adder, this adder, this adder. Okay, so what have you been told? You have been told to find the frequency, this maximum frequency of operation, right? Or the maximum sampling frequency. In order to find the maximum sampling frequency of a circuit, what do you need to find? What is the exact term that I want to know? I want to know from you. What is the term for the circuit called, which I need to know? Something related to time, some path.
It's uh, the critical path delay.
Okay, yeah, is the critical path delay good? Okay, so it's the critical path delay. So can anybody tell? Okay, so can anybody tell me what's the critical path over here? Okay, so let me tell it out. Let us look at the various opportunities over here. I should look for the longest path. Okay, longest path between the delays, or between delay to output, or between input to delay, or delay to delay. Okay, so without wasting much of a time, we know that these are FIR filters. Okay, FIR filter, and what did we find that day? That this was the longest path. Okay, this was the longest path, this was the longest path. Okay, now what do you see? I go to the output over here, I go to the output over here, I go to the output over here. So all of them, all these three paths, you see how many multipliers are there? One multiplier. Now how many adders are there? 1 2 3 4, four adders. Even if you count 1 2 3 4, 1 2 3, oh, this one is 3, so this is not the shortest path. These and this, these are the critical paths because they take the longest time, highest number of delay stages. So there are 4 delays, Tm plus 4 Ta. So Tmax equals to Tm plus 4 Ta. And now what was Tm? Sorry. So what was Tm? Tm was 10 microseconds and Ta is 5 microseconds. Tm was 10 microseconds and Ta was 5 microseconds. So what's the value? 10 plus 4 times 5, that's 10 plus 20 is 30 microseconds. So now if you try to find the, oh sorry, it should be T min. So F max, because you can have any delay greater than this, F max has to be 1 upon T min. What is that? 30 microseconds. Microseconds I convert them back into the power minus 6. So that's okay. So it's like 33.33 kilohertz. Or if you look at the options, yeah, it's obvious. C and D is the frequency, it's not frequency, it's time. C and D is wrong, and B it's kilohertz, so it's 0.003, 0.01123, yeah, megahertz. So it's option A. So Anup, is this clear how we have got this answer?
Yes, yes,
Yes,
sir.
sir.
Good,
Thank you, sir.
welcome. So this was something. Yes. Any other doubt? Question? Does anybody have any doubt in question 4? It's pretty obvious. Okay. This one, does anybody have any doubt? Pretty simple. There are in part A there is only a single input and single output, so it's SISO. Part B there are multiple inputs, multiple outputs, so it's MIMO, MIMO. This one, does anybody have any doubt?
Yeah, actually, can you explain this? Like,
Okay, yeah.
Yeah,
explain
yes,
this
sir.
a little bit.
Yeah. Let me look at this and then, yeah. Okay, so this is a very interesting thing actually. XN. So we have these delays. Did we? Okay, so you multiply them and then delay. So multiply then delay. Okay. B0, B1, B2 and B3. Okay, so I multiply, then a delay, then an add, then a delay, then another add, then another delay, then another add, then another delay, then okay, then another delay, inner delay y of n. Good. So first let's try to write the equation of yn. What do you see? Yn is a sum of lot of terms. So if we look at this, let me take the laser pointer out. So if you look at this, b0 into x of n goes to y of n. Is the path visible?
Yes, sir.
Yes.
Okay, b0 x of n directly goes into it. b0 x of n, and in the next path b0 delay 1, delay 2, delay 3, delay 4, delay 5, delay 6. 6 delays. I'm crossing 6 delays, plus b0 x of n minus 6. Now see what do I do. Then we have the b1 term, and b1 term is after the x of n.
One delay.
Wait.
Sir, V1 now.
Let me check once. Okay, b0 is going. b0 b1. Okay, b0 xn plus. No, okay, no issues. I was just a bit confused. b1 times x. Oops, sorry. X of n minus 1. Yeah, b0. Yeah, actually this b0 xn times b1 xn minus 1 plus. Wait a second. Let me check. Let me check it somewhere else. I mean, there's some issue going on over this. Okay, so there's b0 xn, b1 xn, b2 xn. b1 xn, b2 x. Okay, b2 times b0. Oh, I got yeah, I got it now. So what is happening? Oh no, it's not b0 xn minus 1. Yeah, so I was visualizing it the other way. It's x of n first goes to b1, then 1 delay, 2 delay, 3 delay, 4 delay, 5 delay. Okay, 5 delays are there. b1 xn minus 5, and over here b1 xn, this jump, and then 1 delay. Is this path clear? First we have b0
Yes, sir.
xn going over here, then b0, all the 6 delays are encountered, so this gives the b0 xn minus 6, and then b1 xn minus 5 gives us this term, and then b1 xn minus 1 gives us this term. Okay, similarly now I hope you can understand the pattern. b2 xn minus 2 plus b2 xn minus 3, b2 xn 1 2 3 4. Yeah, it will be 4. xn minus 4, and then similarly the other way, and then the last one b3 xn minus 3, only a single path, plus b3 xn minus 3. Now if I try to write the impulse response or the transfer function, what do I get? It's b0 plus b1 z inverse plus b2 z to the power minus 2 plus b3 z to the power minus 3 plus b2 z to the power minus 4 plus b1 z to the power minus 5, b0 z to the power minus 6. And if I write it as h of n, b0, b1, b2, b3, b2, b1, b0. So what is happening over there? You observe that this actually follows some kind of a symmetry. H of n is h of m minus n, and this symmetry is called linear phase, which I taught in the previous day. So did you understand why it's a linear phase filter? Because the it's a event type linear phase, type 1. Type 1 because there is an odd number of coefficients and it is even symmetric. b0 b0, it's not b0 minus b0, it's b0 and b0, b1 and b1, b2 and b2. There's a mirror symmetry and positive symmetry. That's why it's a type 1 linear phase filter. And since there are 7 coefficients, so 7 tap, hence 7 tap linear phase, type 1. Any doubt in this? Anything that's not clear?
No, no, sir. Sir, your concept is so clear.
I had one question. So what if it was b of n minus 6? Like it was the function we got was b to n, like there were only two terms.
Huh.
There's b0 xn and b0 xn minus 6.
Hmm.
In that case, how many tap filter would it be? And the other terms are not there.
b0, acha. Okay, so you're saying then it would be 2 taps because you are just taking out b0
Okay,
xn and
got it.
b0 xn minus 6 because there is 2 multiplications are there. I guess based on that, because the tap term is actually a bit confusing. Somebody may call it because initially when I saw this, I would have called it a 4 tap because there are 4 multipliers, you're tapping in 4 of them. But the tap definition is actually not given anywhere. What do you mean by a tap? So it might be a bit controversial.
Okay.
Yes, sir. Because I have already uh, discussed about this type of question. How can we define this is 4 tab, this is 7 tab?
Yeah, actually it's a bit confusion. Here the confusion is even yeah. So in general case, like if you have h of z is b0 plus b1 z inverse plus b2 z to the power minus 2, then you actually it's a 3 tap filter. But then actually sometimes there is a confusion because yeah, like in this case there are 4 multipliers, so it could have been called, that's why they had given the 4 tap case as well, but the answer is given 7 tap. So maybe there might be some reason why they are saying this, but if you look for standard textbooks, then they don't directly say anything about this. Okay, so it's a bit on the tricky side.
Okay, sir.
Because it's a these are nomenclature things, it's not much more of concepts, it's more historical and terminologies, so there always lies some kind of a debate. This one, I think this one you might require any help. Has anybody been able to solve this, or does anybody require help in this one? No one? Everybody has been able to solve this one? Anup Pandey, Jagannath Prasad, Saranya, Shashank, Yash Agarwal, Soni, Sonali.
Sir, answer is
Yes, we have been
10.
able to solve it.
Means everybody is able to solve this. Anybody is any doubt?
Sir, it will be better if you
Yeah,
solve this question.
yeah, yeah. So basically, it actually requires the concept of pipelining. So yeah, let me mute. So actually, sometimes it so happens that while doing signal processing, we forget that we are actually implementing it on a real system. So what is happening whenever you have some kind of a multiplier? So if you have seen the structures of these Brown array and Bauli multipliers, so all of them contain AND gates in creating the partial products, and then these partial products, when you are adding them, okay, these are nothing but full adders. And what are the full adders? Full adders are XOR gates, A XOR B XOR C, giving the sums terms, and then you have the product terms as well. Okay, A B B C C A. Okay, A B C. I'm not showing you the most efficient implementation of the full adder, but this is just for your knowledge. You can make it more efficient as well. Sum and carry terms. So what are these? Just I'm just doing a small recap to understand where you are, which subject you are actually learning. So it's encompassing everything. These are gates. And what are gates actually made of? Since we are dealing with CMOS technology, so whenever you're dealing with A's or B, so here A AB plus A bar B bar whole bar. I hope, yeah. So it's NOR of AB. Okay.
Hmm.
Yeah,
So that's exclusive, all right? It's
yeah.
AB. Yeah,
So
correct.
yeah,
It's like
Zwin is
nor a
just
complement of it, right?
yeah, yeah,
Yeah.
yeah, yeah, yeah. Yeah. So basically, my motive behind showing the suddenly why I'm going to digital gates is not just anything abstract or super, not anything abstract. My motivation behind this is that whatever you're implementing in real actually gets implemented in real life in circuits, and you also need to have a good idea of how circuits operate, because at the end of the day, it is these circuits which determine the speed of your signal processing systems. So
Yes.
in fact, if you see, deep learning is growing at a very rapid rate. These applications are now playing a huge impact in our lives. But the concepts of deep learning can be considered as a signal processing field of signal processing to a certain extent. Deep learning was there way back in 1980s. There was this concept of multi-layer perceptrons, neurons. But then, why weren't they a big success? There were three factors, out of which one very big factor was the availability of silicon devices, the availability of this hardware. And this hardware later came because of the Moore's law. Okay, these GPUs, high performance GPUs, CPUs, and new FPGAs are coming. So all of them are helping us in performing all these advanced and heavy computational tasks. So although signal processing in a lighter sense also um, includes a simpler version of these operations, but then all of them rely on the advancement in technology, and by technology I mean VLSI technology. So it's very important that you understand that while you are studying these signals and signal processing courses, you also take some courses on VLSI as well. That will give you a much richer idea. So this was our AB. And in fact, I come from a purely VLSI background, but I had taken courses both on signal processing as well as VLSI. So I got a good appreciation of both these fields in my dual degree program, as well as my PhD also is at the intersection of both these fields. So you understand very well that these are PMOSes and NMOSes, and as a result of which these MOSFETs, if you have studied them, or you will be studying in the next semesters, they have capacitances within them. Okay, Anup, are you finding this clear? Have you studied MOSFETs and their capacitances?
Yes, sir. Yes, sir.
Oh yeah, so you must be knowing this is CGD, CGS, CGD,
Yeah,
CDB,
exactly, sir.
CSB. Okay, so these capacitances,
Hmm.
okay, these capacitances at these nodes, you sum them up and you get this load capacity, the intrinsic load capacitance of the gate. Okay, and it is these load capacitances that manifest over here, and these full adders, as a result they have these capacitances, and when you connect them together they also have their own capacitances. Okay, so as a result of which the multiplier has its own capacitance and adder has its own capacitance. So I hope I have been able to explain everybody how come these so-called multipliers using which we will multiply numbers on our calculators, or we are doing these things b0, b0, b1, we are talking about this. How come all of a sudden we get into a capacitor? I hope I have been able to motivate you in understanding this. So basically what is happening, whenever you have a filter, let's say h of z, I will represent this now as h of z and a capacitor. Okay, so now in one clock cycle between between the two edges, what happens is that there are h of z is let's say 16-bit, the output is a 16-bit number, and by 16-bit there means that there are 16 load capacitances. Clear? 16 load capacitances because there are 16 output lines. Now as you perform some operation, you get some number, let's say 54, and then you convert in, in binary it's something like 0 1 0 0 0, something like this. Okay, so accordingly, let's say in previous cycle your output was 54, next cycle your output is 32, the filter is giving this output, next cycle your output is minus 12. Okay, so you see there is always some kind of switching happening. Okay, these are wrong values, but I am just showing them for the sake of understanding. Okay, so you see values are switching, right? One is becoming, one is remaining 1, one is going to 0, MSB is changing. You see there is a lot of switching activity happening. So the each capacitor is either charging or discharging, and this has to happen within one clock cycle. Okay, so h of z capacitor in one clock cycle, this entire operation has to take place. Okay, now when you have this h of z, if we break it down further, we have multipliers. Let's say I have some structure like this. Now my final output is actually over here, right? But then in order to ensure that I get a proper output, I have to ensure that all the calculations over here occur properly, right? I have to ensure that all the calculations at the intermediate nodes of the critical path, this multiplier, this adder, this adder, this adder, they all have to take properly. That means that in middle, when you do a multiplication and addition, there will be some intermediate switching because the operations are taking place. Okay, so when you do when you actually do Verilog, when you do simulations on Verilog, after doing this behavioral synthesis, you have something called the logic synthesis. Okay, so when you actually use these and when you use the logic gates real implementation, I am not discussing further, otherwise I'll be going to a different course. In fact, when you implement the logic gates real behavior, then you will see that there are intermediate value switching. So you'll get C2, 3, 4, something like this switching. After some time, the value stabilizes. So you have to ensure that all the values in the intermediate nodes stabilize. That means all the charging and discharging along the critical path has to take place. Okay, and along the critical path, most important thing is along the critical path, all of them has to be charged and discharged properly. So that means that the C charge will be sum of all the load capacitors on the critical path. That means in one clock period, what is the maximum path between the 2 points, and those capacitors have to be charged together, okay, within time. Now what will happen, let's say in our FIR filter. Okay, so let's suppose this is a FIR filter. So the critical path that you can see over here is this. Okay, so by putting a delay, I have ensured that I don't have to go through this long path. So then how much do you need to charge? You need to charge the maximum critical path, that is multiplier plus adder. Clear? So let us look at the problem that we are seeing over here. See, here there are two filters. In both the see x of 2k to y of 2k plus 1, the critical path is, you can see it, there is a one multiplier from h1 and then it goes down. There's an arrow. Can you see that arrow, dotted arrow in the diagram?
Yes.
This dotted arrow is actually the critical path. So the critical path shows what are the capacitances. One multiplier, so there was one multiplier and two adder, so the C charge would be Cm plus 2 Ca, and it was said that Cm equal to 8 Ca, so it turns out to be 10 Ca. I hope that was the answer. Yeah, is it clear to everyone?
So how did we identify the critical path? Like, is it already given in the question or we identified it?
Actually, critical path calculation I had mentioned in the previous week's lecture, where I had told that actually you have to keep on searching. You have to keep on searching. By keep on searching, if I look at the previous, yeah. So as I told in the previous lecture, uh, that you have to look for the all the paths. Okay, you have to look for the wait, it was something, it was somewhere else. Let me check. hmm. Yeah, so if you go to the previous week's video, then you have seen that here we were checking each and every path possible. Okay, 1 2 3 4, you keep on checking the paths, or if you keep on practicing the problems, you will get an idea of which is the longest possible path without any delay. Okay, so you need to check paths between xn and yn, xn and delay, delay and delay, delay and yn, and the intermediate paths do not have any delay element. Okay, so you check for the paths, and the one that has the maximum delay in the sense not d but tm plus ta, that delay. Okay, that is the critical path delay. Is that clear?
Yes, sir. Can you please tell me where are the videos located? I will see them. I am not sure. Like, I was posted the link in my chat, in my group WhatsApp, and I joined it. Can you please mention some details about the videos where I'll find them?
Yeah, if you go to the if you go to a SWAM portal and get into the NPTEL, that our RTSP course, there will be something called, there are week 1, week 2, week 3, 4, all the contents are mentioned, right? Where you get able to see the videos. There's that.
So what is the name? SWAYAMs, what was NPTEL SWAYAM, and what is the course's name?
Wait, are you joining? Um, okay. So actually, you have to register for you have to actually go to SWAM portal and register for this course name. Let me show the course there. I can see the course name, real time digital signal processing. Yes.
Yes, sir. Yes.
Yeah, so you have to go to SWAM and then search for this. You search for this course, you can enroll in it. Once you enroll in it, you will be able to see a portion. Yes, you are from IIT Kharagpur, right?
Yes, sir. Yes.
Oh, yeah, don't worry, I'll be sending that batch. I'll be sending it through one of your friends. And in general, for those who are, in case you're not able to find this link, so you can go to the SWAM portal and register for this real-time digital signal processing course. and over there you will have the wherever you have the weekly contents in that column, you will be able to see two places. One is the course material and the other one is live sessions. So if you click on live sessions, you will be redirected to a Google Drive link. Let me share the Google. um, okay, I'll do that later, maybe. Yeah, I'll do that later before the session ends today, and then you'll be able to access the everyday recorded videos. Okay,
Okay,
so
sir. Thank you, sir.
welcome. So yeah, so does anybody have any question? Was 8 clear to everyone?
Yes.
Yeah, good. Yeah, so 9 and 10, anybody have any issue? It's just a straightforward question. It was given, it's nothing much to solve over here.
10th one, can you explain a bit like
Okay,
how it works?
oh, okay, here it's a it's actually it's not a signal flow graph, it's a DFG, data flow graph, it seems. Okay. Hmm. Okay, good. Well, my one of my suggestions would be that apart from this course, you can also view the course on VLSI for signal processing by Professor Mrityunjay Chakraborty on NPTEL. He has covered all the all the concepts on these pipelining, parallel processing in a greater detail. Okay, and in the previous week I also shared a book by Professor Keshav K. Pari on this by the same note by VLSI for digital signal processing systems, which covers a good deal of material that we are studying now.
Actually, is the focus of this course on VLSI signal processing, or is it on the software coding of it, or both?
Mm, Actually, if you see, it's mixed. I mean, in the first few weeks we have been dealing more with the um, VLSI portion. I mean, I am actually, since I'm the PMRF TA, so I am pushing it more towards the VLSI, but yes, there is VLSI signal processing involved in the first few parts. In the middle portion, you slowly go into the software part, and the last is applications, where you don't get to see much of VLSI. It's like there's a practical approach using this code composer studio and all, and a bit of theory as well. So I'll
Okay,
be
thank you.
covering the theory portion, and I might be as somebody said, I will be doing some more practice problems if required, and I might be covering some extra topics as well, which may not be covered in this, which are not covered in this course, but yeah, it will be surely helpful if you are planning for maybe plan to do masters or some projects in VLSI in signal processing. Okay, so what we had over here was something like this. So actually what happens in such a case, let me okay, good. A, B, Z inverse, Z inverse, C. So let me introduce you to this conception, what happens over here. In the earlier, if you look at the earlier filter structures that I had drawn over here, I have shown an explicit multiplier symbol, I have shown an explicit D symbol, an explicit plus symbol. Okay, these are, and this is a block diagram kind of a view, but then there's another view over where we are not showing the multipliers, we are just showing them as simple. We are showing this is a node, this is the edge. Now this view is called an SFG, or a signal flow graph. So what happens over here is that edge can perform delay as well as multiplication. Okay, so you can have a delay, you can have a multiplication. So this is a Z inverse is a delay, or D. If you have multiplication, you write simply write a number over it. If you want to do multiplication and delay, now you can't do it, you have to do it separately. You can do multiple delays in a single stage MD, which means MZ inverse. Okay, now what is happening over here? You see some kinds of nodes. Node gets in and gives out data. Okay, single node is coming in and multiple nodes are coming out. These are called source nodes and also called splitters. Sorry, this is not a source node. I'm extremely sorry, this is not a source node because it's getting an input. These are called splitter nodes, where data comes in and simply flows out. Okay, no operation happening. And then in case you view something like this, where this is an adder node, although the addition sign is not visible, whenever you see multiple edges converging into a node, it's an adder node. So basically you are adding multiple things over here. Okay, so that's an adder node and this is a splitter node. So let me tell you which are the splitter nodes over here. See, here it's going in and things are coming out. Okay, so it's a splitter node. Here also things are going in. Once one thing is going in and two edges are coming out, so it's a splitter node. Here also one thing is going in, one thing has come out, it's a splitter node. Now splitter nodes, as you can understand, when you take from one single wire and break that out into two wires, means two wires are coming out, so you are not doing any computation, so there is no delay involved. But then over here the multiplier has been replaced by a single edge along with the multiplier written on the edge. Okay, this is a multiplier. This is also a multiplier. This is also a multiplier. And then you have these. So this is not doing anything, so you can ignore this. But then see over here, two inputs and one output, so it's an adder node. Two inputs and one output, there is adder node. Okay, so whenever you see something like this, replace it by this. Whenever you see something like this, replace it by an adder, so that things don't get confusing. And whenever you get something like this, replace it by this. Okay, so in the given structure, which one gives one multiplier and one adder delay. So if you can see in adder, in the structure 1, there are 3 multipliers and okay, so there were 2 Z inverses, 1, 2, 3. So there's one multiplier and there's no delay in it, so this is a critical path, Tm plus Ta. Is this clear? Shashank, Yash, is this clear?
Yes.
Okay.
Yes.
Yes.
TM plus
Yes.
TA.
Now we do something called transposition. So what we do, we reverse the edges. Okay, so this entire diagram, all the edges get reversed, goes up. See, these were going down, sorry, these were going down, now I am making them go up. This was going down, now I am making them go up. This was going right, they are going left. Okay, so in a similar fashion I put them, but put the delays as it is wherever they are, don't change their position, that's very important. And now you see, replace the output by the input and replace the input by the output. Okay, so now let's check our critical path. So this one multiplier adder, multiplier adder, multiplier adder. So it's Tm plus Ta. So you see over here, by doing a simple transposition, I have reduced the critical path of my system. No use of any feed forward pipelining, no use of extra delays. Okay, and this is the one which has a 1 multiplier 1 added critical path.
Actually, I had a doubt. Can you go back to that slide,
Yes.
please? Which you were showing. Yeah. So from here, if you go from xn to yn, right? So if you go
Hmm.
from xn to c,
Hmm.
xn through c, and then there are two adders, right? From xn to c, and then again through the two delays. If we go z
We
inverse and z
we
inverse.
can't cross the z inverses. They are delays. So whenever you talk about critical path, it is a delay free. You have to go through a delay free
Oh,
path.
okay, got it, got it.
Though you can't have, because whenever you delay, your delay is safeguarding you from that timing violations and all those things. Understand, right? Okay, let me say it in simple
Yes,
word.
yes, understood.
Okay, okay. So
It's
those,
a flip flop.
yeah, it's a, yeah. So
Yeah.
as and always, I will always mention this, and it has been a fascinating part of my life. When I heard this, I was shocked. So basically, a z inverse is nothing but a set of flip flops, also called registers. Okay, I had mentioned this in my previous classes as well. So you have, let's say, xn as a some 5-bit number, x0, x1, x2, x3, x4. All of them are being stored, going through this clocked sequential element, synchronous sequential element. We are dealing with synchronous elements only. Okay, so that's it. That's the delay element. Okay. Does anybody have any doubt? Any other questions on this? So yeah, I mean the previous assignments. Okay, so basically we were to discuss about IIR filters. IIR filters are so not much different, but okay. So the general structure goes as follows. So basically, yeah. So an interesting thing to mention, you can never have a direct loop like this. Or let's say, even if you add a multiplier, you should never have some kind of a delay free loops are not allowed in DSP. Not even DSP, in control systems as well. Everywhere delay free loops are not allowed. Why? If you look at them, yn is xn plus ayn. So there's a continuous kind of a feedback. So xn is coming in, yn, let's say it was 0. I mean, you can't store any value, so it's like an indeterministic. Yn becomes, let's say yn is 2, xn is 1, then 2 into something, let's say a 2a plus 1, 2a plus 1 comes in. Okay, let me say it in a more simpler manner. Let's say xn is 1 always. Okay, and yn is 0. So when yn is 0, yn becomes 1 plus a into 0, 1. Yn becomes, here yn becomes 1, xn is 1, a into 1, 1 plus a, yn becomes 1 plus a into a plus 1, a square plus a plus 1. So you see, within a few instance of time, your input actually keeps on rampantly rising, and then you will reach saturation. So basically, such loops are actually unstable, and you're not supposed to create them. It does not serve any purpose. Okay, so you have yn, then you have the first delay element a1, that's the first coefficient, a2, second coefficient all the way till an goes up. So what happens? Yn is xn plus a1 yn minus 1. I hope you understand why. Yn getting delayed, yn minus 1 multiplied by a1, then going to the other. Okay. Similarly, yn going to 2 delays multiplied by a2, then going to the other, and so on. You can see for this as well. Plus a2 y of n minus 2 plus so on till an y of n minus n. So when I take the z inverse and I put these terms, x of z, a1 z inverse yz all the way till an z minus n yz, taking then to the left side, yz 1 minus a1 z inverse as a2 z inverse minus an z inverse, so x of z, h of z, yz by x of z gives you 1 minus a1 z inverse minus a2 z inverse minus an z3 by minus n. Oh, that will denominator. Fine. So this is our so-called IIR filter. Even if you have an FIR filter followed by an IIR filter, this combination is also an IIR filter, because it's finally the impulse response that matters. The 1 plus some constant 1 plus b1 z inverse plus b2 z inverse 1 minus a1 z inverse minus a2 z2 minus 2. So even though these terms are finite, when you actually expand them, and because of the denominator, there will be infinite number of delay terms. Okay, so that's why k belongs to 0 to infinity. This is an infinite length response. Okay, and there are two primary implementation methods. There are multiple, but I am saying the two primary. First is the direct form 1. What happens over here? Here b0, this section I will tell you soon what is this section doing. b1 all the way till bm. Guys, can you see some familiar structure over here? We have been dealing with this for the last 2 to 3 weeks. What is this structure?
A fire filter.
Absolutely, this is a FIR filter. And what does this FIR filter give us? Poles or zeros?
Zeros.
Absolutely, FIR filter gives us the zeros. But then actually in reality, if you see, FIR filter will give us zeros, will give us, it can give us real zeros. We saw in our week 2 assignment 1 that we had this 5 minus 5 z inverse. So yes, and then we continue this. With the section that we had drawn earlier, delay a1 delay a2 an. So this was the structure that I drew few minutes back over here, right, is the IIR portion which gives us the poles. Now an important part to note over here is that here there are m storage elements, here there are n storage elements. Storage elements or registers, same thing. So there are how many total storage elements? M plus n storage elements, and then you have these adders over here. It's fine, but now let's look at another possible implementation. Is the number of storage elements clear? Why it's m and why m plus n? You have m.
Yes, sir.
Okay.
Yes.
Okay. So in case anybody has any problem, don't hesitate to tell me, even if you are not able to understand a single thing. Okay. So now let me copy this portion. Okay. Copy image, screenshot. Okay. Now I do something interesting. The same structure that we used in the previous one, we shall be doing it over here. So you see over here there was a delay down and there was an A1 over here coming in, delay here and A1 coming down. Now what I want to do, I put this FIR over here and I put this IIR over here. Simply it's a cascade of two linear systems. So when you do cascading, then they will switch the position, but the transfer function won't change, right? Good. So then what do we have? Yeah. A1 A2. Let's say for some reason the number of delays on this side are more, an minus 1, an. Okay, now see the difference. How many delays are required over here? If this section has this is an mth so portion and this is the nth order portion, how many do I require? Let's say if m is less than n. Absolutely. So actually in general you have maximum of m comma n elements. So if you talk in terms of number of elements or area, so number of adders are same, number of multipliers are same in both. This okay, this is called direct form 2. This is called direct form 2, and what happens is that the number of multipliers and adders are the same, but then the number of registers in direct form 2 is actually much lower than the direct form 1. Okay, so in terms of area and power, direct form 2 seems to be much more better than direct form 1, but then there are other parameters such as every filter has its own noise characteristic. By noise characteristic I mean that if you look at these adders and multipliers, so what happens is that we are fixing the output to certain number of bits. Let's say I multiply a okay, so in order to illustrate this, let me show something. xn, yn and a. Okay, so this, let's suppose, is an 8-bit number. This I suppose, let's keep this also 8, let's keep this also 8. So product of an m bit and n bit number we discussed in the first week was m plus n bits, right? So this is a m bit 8 bit, and this is also 8 bit, so we have 16 bits, 16. But then what do we see? We see that we have an 8 bit and 16 bit number, but then we are truncating the output to 8 bits. So what is happening whenever you are truncating or you are doing rounding of the number, you are actually introducing injecting some kind of an error. Okay, this is called quantization error. Round off error, sorry, it's not called quantization error. Quantization error takes place in the input because of the A to D converter, but then this is the round off error. Okay, so every filter has its own characteristic error because you are truncating things over here. So in that case, there's a detail and way in which you can analyze the rounding off or does noise due to these truncations. Okay, which we shall not be dealing with in this course, but then you need to analyze and check whether direct form 1 is better than direct form 2, and there are various other implementations like SOS is called second order section. So what you do over here is that you how does it look like? Okay, actually kind of take you can see over here that it's a second order IIR filter. Okay, and we call this as SOS second order filter. So you take multiple SOS and put them in cascade. So sometimes what we do is that in general we actually go for this kind of an implementation because it has very low noise properties. It does not increase compared to direct form 1 and direct form 2. You can actually design them in such a way that your noise is very low. Okay, and in fact if you have gone through this week's lecture, if you go to next week's lecture, you will be able to see that it is SOS will have some pole zeros. Okay, we call them pole zero pair. So if you have a filter which has multiple poles and multiple zeros, what we do is that, let's say there are okay, so what happens is that, let me clear them, let me rather put them in different location. What happens is that you can see there are 3 pole pairs and there are 3 zero pairs. Okay, so you can do lots of permutation combination and create multiple types of second order section. So let's say you can pair this pole and this zero pair and create a SOS, or you can take this and pair it with this, or you can take this and pair it with this. Okay, is it clear what do I mean by pole zero pairing? This is the SOS. Huh? Is it clear? Hello.
Yes, sir.
Okay, so these are the pole corresponding to this section. We have a pole and zero
Yes.
pair, and what is actually done is that first we try to take that pair, pole and zero pair, which is closest to the unit circle. So closest to the unit circle is these two, so I take this as my first one. Then which one is the next closest that I can see? This blue one, this one. And then over here, can you please hold on for a while? Actually you just got a call. Okay, just coming in a few minutes. Hello,
Uh,
Gagan. I'm audible, right?
it's not. It's not very audible actually. You need to bring the mic close.
Hello, hello.
Yeah.
It's
Yeah.
audible.
It's fine.
Okay. So you understood the closest poles was this purple one, then the blue one, then the green one. Okay. So based on that, we have 1, 2, and 3. Okay. Then we pair up 1, 2, and 3. Okay, in this order. We pair up. We take these poles and zeros and create the first SOS. Then we take this pair, this blue one, and then create this SOS, and then third one, and then create this SOS. And again, among, you can also arrange them in 1 2 3 2 3 1 3 1 2. Okay, and then there is 1 second you will see in the lecture something like which method, in which way you have to arrange them. So there is something like L2 norm and that thing. So that I is it okay if I discuss it in the next week? The power means how do I arrange these poles and zeros or the SOS sections. I will be discussing that in next week. Okay.
Yes.
Okay. So does anybody have any other doubt?
Excuse me, can you please share share the details of the
Yeah,
problem sheet?
yeah. Problem. So basically, actually, I have a lot of material to show you guys. Acha. So over here, as you can see here, every day I will give the YouTube links, and you will be able to check it. And if you visit my web page over here, and over here, if you go to the um, uh, educational background, oh sorry, coursework, sorry. If you go to my website over here, pmrfshouharda.com, and you go to the coursework, then you will be able to see a lots of courses: VLSI signal processing, VLSI interconnects, technology modeling, a lot of signal processing courses and VLSI courses that I had taken in the past years, whose materials are available with me. You can surely access them for your good use. Okay. So does anybody have any further doubts? Okay, I'm stopping the recording.